either product or quotient, depending on what you want to look at it. Look at it with. Let's see if we can see that in the Excel sheet. Let's see if we can see that in the Excel sheet, okay? Let's see if we can see that. Let's pull this down. Or quotient, yeah, quotient, product or quotient. Yeah, these rooms being as wide as they are is not always helpful. Let's keep this up. All right. So Echo, I'm going to slide your prediction over. Your prediction is actually what Gabe's talking about, is that perfect fit. Okay, so let's look at the first quotient. I'm going to use quotient if you don't mind, because what I'm going to do is I'm going to divide this one by this one, which I think is an easier way than trying to do some kind of weird inverse multiplication. So what I'm going to do is I'm going to do equals this number divided by that number. Then I'm going to drag this bad boy straight down. Now take a look at these numbers, friends. Let's make it a little more obvious. Let's round them off. Let's round those numbers off to, say, 2 decimal places. Are you seeing any kind of a consistency there? Now, they're not perfect. They're not perfect. They're not perfect. But they're all hovering right around a half, aren't they? That's the harbinger of an exponential relationship. You're going down by roughly a half each time. Each one is being multiplied, not added, but multiplied by the same thing. That's your exponential. So a constant first quotient or product is one way of looking for exponentials. How about graphically? How about graphically? We all thought this was quadratic when we started, didn't we? We all thought this was quadratic when we started. Let's blank this out, go back to our graph. We all thought this thing was quadratic. But what was the problem with the quadratic fit, if you remember? So, how does the graph of an exponential function differ than the graph of a quadratic function? How do the graphs differ? Maddie?
I don't know.
Oh, I thought your pencil going like this. I thought you were saying yes. You're trying to process it. That's totally fine. How is this exponential graph going to? It's definitely similar to a quadratic in that it's got this kind of curve to it. But how is it different? Penelope, go ahead.
Once it hits 0, it's not going to go back up.
It's not going to go. Actually, you said 2 awesome things there. Once it approaches 0, it's not going to go back up away from 0. Quadratics, parabolas are symmetric like this. Once it gets close to 0, it's going to continue on that path, getting closer and closer and closer. Now I know, let's get back to the graph here so you can see it. I know that in our example, you can't get closer and closer and closer and closer, because once we've got 0 heads, we've got 0 heads. But mathematically speaking, we're getting close to your perfect fit, Gabe. 38 becomes 19. 19 becomes 9.5. 9.5 becomes 4 3/8 or whatever it is, 4 and whatever the 4. 4.5 becomes half of 4.5, becomes half of 4.5, becomes half of 4.5. What does that never equal? It never gets to 0, but it gets as close as you want it to get to 0. So let's answer Gabe's question now. In the Y2 spot, I'm going to put in the perfect relationship of 38 coins times 0.5 to the x power. So in other words, this beautiful model right here was our experimental model. What I want to put in next is the perfect model, 38 times 1/2 to the x. This will represent exactly 1/2 of the coins disappearing each time, which I know we can't do, can we? You can have half of 38 become 19. We did it in one trial. 38 became 19. But once you go to 19, we can't have exactly half of them disappear, can we? It's an odd number. You can't take half of an odd number and have a whole number left behind. But on average, you can. On average, you can. That's the point. You ready? Hit graph. Hit graph. What do you notice? Look how close. Exactly, Jen. It's this close. It's so very, very close to our data fit model. Meaning that I think we did a damn good job calling our exponential up here. Yeah, Ben, you totally had it. But I got a feeling that most of us haven't seen exponential models before, or even exponential equations before. The big difference algebraically is when you have a linear or a quadratic model, the variable is in line and the exponents are numerical. Janae, you said that earlier today. You said look for the exponent 2 or 1 or whatever it was. Perfect. Now, the variable is the exponent. That's what makes exponential models different. The variable itself is the exponent. That's what makes it interesting. The variable itself becomes the exponent. Yeah? Ish? I'll tell you what. I got an idea. You're starting to get that total glaze look right now. I think we're done with the coin flipping. You enjoyed it at first. I think we're past enjoying it. What I'll do, we'll call it a day. I want to look at student loan debt. I want to look at student loan debt, which will depress the shit out of you. I also want to look at U.S. population. I want to look at a few other things. I want to look at something called the forgetting curve, which is tied to the learning curve. I want to look at a bunch of things that have basically been shown to progress exponentially, because it's the last model I want to look at is the exponential, because it occurs. Now, why did you all grow when I said I want to look at student loan debt?
Because it sucks.
Because it sucks and it applies to a lot of them, I'm assuming, right? So what I want to do is I want to show you something that actually happened a few years back with a student who got himself trapped in student loan debt without understanding exponential growth. And he basically set himself up to never be able to repay his loans. He was paying off his loans, but he wasn't paying off enough from month to month to actually, it's like paying your credit card debt minimum balance every month. You're never going to pay it off that way. Of course, they don't tell you that in the statement, except in very fine print. So what I want to do is I want to look at that kind of stuff next time. I didn't put a quiz up for this week, but I think I have an idea for a quiz for next time, if you want to do it. It'll be kind of an exponential review quiz. I'm thinking like, how many of you need a refresher that anything to the 0 power is 1? Like, was that kind of like, oh, I learned that at some point, but I don't quite, yeah, good. So what I'm thinking maybe is, I get like an exponential review quiz up between now and Thursday. It shouldn't take you more than 10 minutes or 15 minutes to knock out. That way you have a quiz for Thursday. And this solves the problem of not having an exponential modeling quiz posted. How's that sound? Does that sound decent? Yeah, I like that idea. And that way you can do your test corrections too. Exam corrections for Wednesday as well. Okie doke? So let's call it. Let's call it a day.
A little quiz due Thursday.
I will have a quiz posted. It's not posted yet. I will make it when I get back to the office.
But look for it.
Look for it, yes sir. It might not get posted until tomorrow morning.
That's fine. I just want to make sure that I got that.
Okie doke? All right, more on this on Thursday. What's up, Ben?